let's get started. Good. Good. So, last class, we started to talk about Bellman's optimality equation during this finite MVP. So let's just review it very quickly. We have a state space, action space, reward space, transition canal, or function. And you have arbitrary policies, pi, that live in this policy space. And the optimal value function was defined as the best value that you can get state-wise if you're optimizing policies for every single state. And the theorem that we are trying to prove was saying that this optimal value function satisfies a beautiful identity. It's the value that it takes at some state S is the maximum value that you can get if you're considering all possible actions. And then you take the immediate reward function. So the immediate reward function is derived from this kernel. And another function is derived from this kernel, which is just the transition function for state transitions. Okay, so you have the immediate reward plus gamma. So gamma was your discount factor. They're in continuing task with a discount factor of gamma. And you need to sum over all possible next states of the probability of arriving that state multiplied with the optimal value that you would get if you arrive at that state. And I introduced this notation, this operator that I was writing, that it maps functions from S to R to functions from S to R. And this was just defined with the right-hand sides, but let me just write it out. For any function v, by the way, so this notation, R to the S, just occurred to me. Some people may not have seen it. This is the set of all functions that are mapping from the state which is in the par position to this set which is in the bottom of taking the par. So just this notation. It's a product set. It's like for every value of this set, you get a value from there. What is that? Like that's like a function that selects those values. Okay. And so you take a function in this set, and the operator gives you a new function that if you evaluate that function at some state S, then you would get what's on the right-hand side here. I really need copy-paste on the board, except that here instead of V star, you just have V. So you're kind of like, you have a probe function. Instead of V star, you don't know V star. You just probe that and like, okay, what does this return? And with this operator, of course, the theorem can be written in the equivalent form that V star satisfies this identity that if you apply this operator to it, then you get V star. So functions of this kind that are not changed by some function like an operator, they're called the fixed point of that operator or function. So in cases like this, we say that V star is a fixed point. Of T. The idea is that like T maps functions to functions, and this is a function that if you apply T to, it doesn't change, it's fixed. It's the fixed point of this function, T, or operator. Okay, and last time we talked about, we started the proof of this, and we said that the proof is going to have two steps. In one part, we're going to show that V star is less than equal to T applied to V star. And we are done with that part. Okay, let me write it here. It's too long. So that's one part. And we are done with that. So if you look up the notes that I wrote about this, you will see the details. Last time when I was presenting in the class, I kind of swept a few things under the rug. Implicitly, I kind of assumed that the policies do not depend on the random rewards that you're receiving, for example, just for the sake of simplicity. But even if they do, everything goes through the same way as I said. So this time, let's consider the other inequality. And if you have these two inequalities, then of course, equality must hold between V star and TV star. Because you can just write a chain of like, okay, V star is less than equal to TV star, which is less than equal to V star. So everything has to be equal there. Okay, so to prove this, we start with a simple idea or a simple construction. So the definition of the optimal value function says that, okay, the optimal value at some state S is the value that you would get with the best possible policy that tuned to that state. Okay. I told you that this policy is going to exist, but we don't know it yet. So we can't really talk about that. But we know that there will be some policy which is arbitrarily close to this value. Like it gives you V star S minus epsilon for an arbitrary value of epsilon, right? Because this is the property of supremums. So let's fix some epsilon positive value and fix some state S. Then there exists a policy which depends on S and epsilon. I don't denote the dependence on epsilon, but the dependence on S is going to be important. And so I want to make sure that we understand this policy is dependent on S. So there exists a policy that depends on S such that the value of this policy at S is almost as big as the optimal value, and the gap between them is at most epsilon. So it loses at most epsilon compared to the optimal value. Clearly, if there was no such policy, then that would contradict with that V star S is the supremum, is the least upper bound. Then there would be a smaller least upper bound if this was not true. Okay. So far, so good. So we have all these policies, and we're going to use all these policies, and we will construct a new policy out of these policies. These are going to be the policies that we are going to follow. After one step, we arrive at some state. S, if you arrive at state S or S prime, then you follow this policy, pi S or pi S prime. It like depends on what state you arrive. If you arrive at state 1, you follow pi 1. If you arrive at state 2, you follow pi 2, and so on and so forth. What to do in the first step? Well, what we want to prove is that V star S is equal to this maximum thing. So what we can do here is that we can guess that maybe a good thing for the first step would be just to choose an action which is recommended by looking at this equation, this maximizing like this equation. We choose a maximizing action for the very first step. So pi naught, the very first policy that we're going to, like the policy that we use for the first time step, is going to be this policy that is a deterministic policy. So we are all deterministic policies as well, such that for every state S, pi naught S is going to be a maximizing action. Okay. So these argmax notation, I used it before. It just means the set of all actions which give you the maximum value. Sometimes people also write, oh, okay, so if this is a set, then it should be like this action is in this set. Okay, so that should be element. Sometimes people just loosely, like what I was just doing, write an equality. That kind of means the same. But we don't know whether there are ties between actions. So maybe there is no unique maximizing action. Then like, what's the meaning of argmax? Then it doesn't really have a meaning. You could give it some meaning that ties some broken arbitrary or something like that. But let's just use this with, keep in mind that this is a set. Okay, so then pi naught chooses a maximizing action. And then let's calculate the value of this policy. The hunch is that this is going to be a policy whose value is going to be pretty good. Because at first step, it first of all seems to be choosing something nice. And after the first step, it's going to follow these policies, which are pretty good, right? Like if you could find the policies which give you the optimal value, then you would be done, basically, with the equality. So let's see. So pi is this policy that for t equals naught, t equals 0, use p naught, pi of 0. And then for t greater than equal 1, for when t equals 1, from that point on, use pi, and here, whatever random state you arrive at time step 1, capital S1, use the corresponding policy. This is the policy that we're going to follow. So all these policies satisfy a Bellman equation. So this is a policy which is not a stationary policy because it switches from pi naught to something else. And these other policies are also memory-based or history-dependent. So it's a history-dependent policy. But its value still satisfies a Bellman equation. So the value of that this policy achieves in state S is going to be Usually there is a sum over all the actions, probability that you take that action. But the first time step, we have a deterministic policy. We don't need to write a sum because we deterministically select some action. So we can just like plug in that action directly. So we'll get the immediate reward for time step 0. And then for the subsequent time steps, we have to sum up how much value we're going to get if we arrive at some state S prime with some probability. So if we arrive at state S prime, we arrive there with this probability. Here we are going to use what policy? It's policy pi of S prime, and we arrive at state S prime. Okay, so that's all the future values that we are going to incur if we keep following this policy. Yes. Oh, there is no A here. It's pi naught S. That's correct. Thank you. Okay. Yeah, it is a deterministic policy. That's why we can write pi naught S. We defined it here. Is the greedy policy. Okay, so these things do have a name. So when you're choosing this maximizing thing, maximizing action, with respect to this little calculation that we are doing here, that's called greedy with respect to whatever you write here. So in this case, V star. So this is a greedy policy with respect to V star. Okay. Okay. So now we have this, and we know that this inequality holds. Let's call it 1. Let's give it a number. So by inequality 1, so this inequality says that yp at S is at least as large as V star S minus epsilon. So we can apply this to S prime. So we can replace this by V star at S prime minus epsilon. And we get something less than equal. But let's just do that. Okay. Just chaining inequalities. Again, we are using that these numbers are non-negative. That's why we can do this. Gamma is also non-negative. And now we can distribute the sum over all this subtraction. And the sum of these probabilities sums to 1. So you can pull out the epsilon, and you will have minus gamma epsilon. So let's just write that. Minus gamma epsilon plus R S pi naught S plus gamma times S prime, sum over S prime of P S prime S and pi naught S times V star at S prime. Okay. So this is nothing but due to the definition of pi naught, operator T applied to V star and evaluated at S, which is just a shorthand that like we were taking the maximum over the actions. So just free this, like this is an action, you take the maximum over the actions, that's like this value. So that part is that. So because of that, this is equal to T of V star evaluated at S minus epsilon. So now the epsilon was arbitrary. We can make it an arbitrary non-negative number. We can let it go to 0. And the inequality still needs to hold. This was holding for every epsilon. Therefore, it holds with 0 as well. So it follows that V star S is at least as large as T V star at S. This is gamma epsilon. Yeah. And this holds for every S. So that means that V star as a function, a vector, is at least as large as T applied to V star, which is what we wanted to prove here. V star is at least as large as T V star. That's done. The proof is done. Okay. Pi not S? Pi? Where did I use pi? S1? Like this definition? This definition was used in the very first step when I said that the value function of policy pi satisfies this equation. Because when you arrive at state S1, you take the expectation over that, and that's like denoted here by S prime. So that's the state at time step 1, possible values for the state at step 1. And so you're expanding that expectation here, and you get the S prime over there. Okay. So it just says that, okay, like at that time step, you're following this policy, which was nearly optimal at the state by definition, and you get its value. Okay. All right. So with that, we are done with the proof of this theorem. Awesome. Any questions for this? Yeah.
So that should be S prime.
Which one?
S prime. The V define or R max. There, like S prime is being the index here.
It's S prime. Yeah, correct.
And
yeah.
The second magnitude, isn't that equality in the second line from, because you're just, yes, the next line is just equality.
Oh, this is equality. Yeah. Yeah. Correct. Okay. Good point. I just leave these there so that you guys can discover these things. Not true. Too close to the board, you get blinded. Anyways, okay. So we have this result, but we can say much more. Why do we care about this theorem? Is because once you know the optimal value function, you know how to act. If you have the model of the MDP, if you have the immediate reward function and you have this transition function, then you just need to follow actually this policy, this pi naught policy. That's the next thing. We're going to prove that this is optimal. You don't have to bother with like, oh, like the next time step I have to do something different. You just keep doing this. Like you just fix this policy, this greedy policy with respect to V star, and it's going to be optimal. Okay. We call that the fundamental. I call that the fundamental theorem. of MDPs, discounted MDPs or whatnot, pi naught is optimal. And the other part that I want to add to that, so this fixed point equation holds, TV star is equal to V star. The set of fixed points for some function or operator, I'm going to write for that fixed. Okay, so if let me maybe use this part of the board. If you have a function that maps some set, I don't know, call it x, to some other set x. Could be a set of functions or something else. But it maps the set to the same set, then the set of fixed points for this are those values in x that the function leaves in place. Okay, so that's the notation I'm going to use. And here, I want to claim that t has a fixed point, and its only fixed point is v star. So we're in this very lucky situation that if you solve this fixed point equation, then you get v star, and from v star you can get this policy, this greedy policy with respect to v star, which is going to be an optimal policy. And notice what happened. We defined v star is with the help of all policies, including history-based policies. History was allowed to be used here. And there, we discover that there is always a policy, which is a memoryless policy that doesn't use the history and which is optimal. So what does it mean that a policy is optimal? It means that its value function itself is equal to, for every state, it gives you the optimal values. The value function of this policy is the optimal value function. It's the best possible thing. It's a very unique thing that you can have this. And on the top of it, you can have a memoryless policy that achieves this. It's beautiful. It simplifies life. It simplifies life largely. All right. So let's get on to this. So the proof of this is very simple once we have the right tools. But we need to have some tools. I'm going to develop some tools. It will take some time. Should take 10 minutes because I want to finish this proof. And once we have the tools, we're going to be fine. It will be like a two-line proof. So from this theorem, you can see that we need to study the fixed points of some functions or operators. And a very useful tool for studying fixed points is called the contraction mapping theorem. This is a very powerful result of mathematics, extremely powerful. It's used a lot. It's a very basic result as well. It's so basic that we can learn it in 10 minutes. So to understand this theorem, we need to understand what contractions are. I'll be a little bit more general, not just talk about contractions, but I'm going to talk about Lipschitz functions because it will help us to recognize that we do have contractions. So I'm going to generalize this to Lipschitz. All right. So what's a Lipschitz function? So let's take a function that maps some space X, which has a norm on it, the norm of X, to some space Y, which also has a norm on it. And these X and Y should be vector spaces because otherwise norms are not defined on them. Moment. Like a Euclidean space. You have seen vectors. So if you collect all the vectors into a space, you get a vector space. What can you do with vectors? You can add vectors, you get a vector. You can multiply a vector with a number, you get a vector. The multiplication and the addition has these associative properties and commutative properties, which make the space a vector space. Okay? Just think about Euclidean space, all right? So whenever I say vector space, just think that this is a Euclidean space. Maybe I should just write Euclidean vector space, because you can generalize it to other things, but it's pretty much the same thing, so it doesn't really matter. Generalizations are not super important for us. It will be enough if we know these results for Euclidean spaces. Euclidean vector spaces everyone learned about in linear algebra, right? Okay. Norms. That's the next question. What is a norm? Yeah. By and large, that's kind of the interpretation. If you're in a Euclidean space, usually you use a 2 norm, which is like the sum of the squares of the coordinates of the vector under the square root. This is a 2 norm. That's one example of a norm. There are other norms. The maximum norm is going to be our friend, for example, in this case. But generally, if you're in a Euclidean space, you have a vector there. Then there are this class of norms, the P norms. And the P norm is the generalization of the 2 norm. It's P is a number which is at least as large as 1. And maybe it can go up to infinity. And like you extend it to infinity. And I'll tell you about that. And the way it works is that you're in this n-dimensional space. So you take the coordinates of the vector, you raise them to the power of P, and you take the pth root of the result. When P equals to 2, that's the Euclidean norm that everyone learned about before. So that's just the length of the vectors. Norm is a generalization of this notion of length. So sometimes people want to use different notions of like how long is your vector, because it's more convenient. And another norm, so when P equals infinity, you can take the limit and you can prove that they're actually, like what I'm going to write is what you're going to get if you let P goes to infinity. But there is a very simple expression for the limit of this. The maximum norm, or the infinity norm, is just the maximum for all the coordinates of the vector. It's like the box norm. It's kind of like, okay, you are in 2 dimensions, and you happen to have this vector. So normally, this is the 2 norm, the length of the vector. That's what we think about the norm of the vector. In this case, what you think about is that, okay, like how much deviation do I need to have from 0 and take the largest of those? So this number here, this vector, is going to be the maximum norm. Okay, so this kind of superflows this other component. So that's the maximum norm. So what makes, so norm is generally just a number that you assign to vectors, but it has to satisfy certain properties. What are the properties that it needs to satisfy? It has to be non-negative because it's kind of generalizing length. Also, it has to have this homogeneity property that if you multiply the vector by a real number, then the length of the vector changes by multiplying the length by the absolute value of that real number. So that's called positive homogeneity. And the final property is that you have to have the triangle inequality, right? So we know that if you have one vector, you add another vector to it, you take its norm, that's upper bounded by, that's the length of the sum of the vectors, that's upper bounded by the lengths of the individual vectors. And why do people call that the triangle inequality? Well, you have a triangle here. Doesn't matter how it looks like. Here is one vector, x, and here is, that's not, okay. Here is one vector, x. Here is another vector, y. And this is x plus y, right? So you just follow the two arrows. One arrow, second arrow. The sum of these is this sum, right? You got a triangle, right? Because this x plus y ends in the same quarter as if you first go with x and then y. That gives you a triangle. And we know that in a triangle, normally, you have that, I forget the English names for this, like the longer side, the length of that is at least as large as the length of the two shorter sides. Okay, so that's called the triangle inequality. And it doesn't matter whether you take a Euclidean norm or you take the maximum norm, the triangle inequality holds. It holds for every p norms. You don't call something a norm if the triangle inequality doesn't hold for it. Then you won't even call it a norm. That's just some function. So if you have a norm, the triangle inequality holds for it. Okay. So that just, I don't know. You must have covered in linear algebra norms, right? Okay. Phew, that was 8 minutes. Okay. So if you have these two normed Euclidean vector spaces with possibly different norms, but often the norms are going to be the same. Then you have a map F that maps one space to the other. We say that F is L Lipschitz. L is just some letter that you use. It's a non-negative number. If it holds that for every x and x prime in the domain of x, the distance between where x and x prime go, if you apply f to them in y space, is never larger than L times the distance between where they were in the x space. So the picture that you have in your mind, that you have x, you have y, you have these norms on it. You take 2 points, x and x prime. F is mapping all of these points to all points there, or some points there. So x is mapped there, x prime is mapped there. And this distance here can grow, but it only grows so much. And if these guys get close to each other, then these guys need to come close to each other. Okay? Because look at this. If this goes to 0, then this has to go to 0. Because this is an upper bound on this. Okay? So it follows that if you have a Lipschitz map, it's continuous. If F is Lipschitz, then F is continuous. Other very simple property of Lipschitz maps is that if you take a Lipschitz map and you have another Lipschitz map that goes on this side of the board, So let's say you call it G, and it goes into this space Z. That's also Lipschitz. So now, okay, like you have an expansion of by a factor of L at most, and then you apply G. It can also expand because it's Lipschitz, so G is going to be L prime Lipschitz. So now it can expand a little bit more. But altogether, if you take the two together, F applied first, followed by G being applied, then the total expansion that you can get is at most the product of the two expansions, right? So first time you can expand by a factor of L. Next time, that distance can be further expanded by a factor of L prime. The total expansion by following the two maps is L times L prime. So if F is L Lipschitz and G is L prime Lipschitz, and they can be concatenated, so they are compatible. So G maps the Y space to Z space, blah, blah, blah. Then if you apply G on the top of F, then this is L times L prime Lipschitz. Right. Finally, if you have a map that is L Lipschitz with L less than equal to less than equal to 1, then we say that F is a non-expansion. These are just definitions. And if L is smaller than 1, we say that F is a contraction with contraction factor of L. Okay. So Lipschitz is a big class, non-expansion smaller class, contractions even smaller class. Lipschitz allows some expansion, positive expansion, like greater than 1 expansion. Non-expansion is kind of like just go straight. No expansion is allowed. And contraction means that you're pulling things together. So the contraction mapping theorem, finally we can state it. It's about a map that goes from one normed, let's say, Euclidean vector space to another one. To the same one, because we want to talk about fixed points. And we assume that F is alpha Lipschitz with alpha smaller than 1, so alpha contraction. Then this has some nice consequences for the fixed points of F. So then it follows that the set of fixed points of F has a single element. Okay. And if you take whatever, I don't know, x naught in X, and you create a sequence by applying F to first x naught, then on the result of that application and so on and so forth, so xn plus 1 is equal to f of xn. to create this sequence of points in the space X, then xn converges to some point x star which exists, which is the fixed point. So let's call the set of fixed points of f that's just x star, since we know that there is a unique element of it. So this sequence, no matter how you initialize it, converges to that fixed point. And it also follows that this convergence is super fast. So xn minus x star, you look at the distance between xn and x star. And here I'm just going to stop using this x because it's like a fixed norm. So I don't have two spaces. I only have one space. I don't have to use that complicated notation. So we know that this is smaller than or equal to alpha to the power of n times the distance between x0 and x star. So this is the contraction mapping theorem. And I think I would just need to stop here. We just build up the tools. Once we have the tools, we will apply these tools the next time to show that this happens to be true. And these tools are also going to be extremely useful to understand why value iteration and policy iteration that you have already read about are actually working. Okay? That's going to be the same tools. All right. Next week then. Have a good weekend. You can start the Coursera next module. We have some troubles with the current module. We'll fix it. I hope at least not totally under control at the moment, but we'll work. Right.